This is the Chem 1 lecture for properties of acids and bases. This is Unit 16, so if you have the paper packet, you can open that up. If you have a scratch piece of paper to take notes on, or download the digital version in Google Classroom. But this is the lesson 1 of this unit. And our goals for today are that at the end of this, you should be able to name and write formulas for acids and bases. And so that's going to be a throwback to nomenclature, which we'll do review and practice with. Also be able to list the properties of acids and bases. And then lastly, be able to identify strong versus weak acids and bases. Before we jump into today's notes, I wanted to do a quick review of the charges. We will be using a periodic table, the front and the back. So if you have a paper copy, I would suggest having that out. If you don't, we will post one in Google Classroom, and you can hopefully maybe have a split screen going on. But last semester in the fall, we learned how to scientifically name and write formulas for different sets of compounds, ionic, covalent, and acidic compounds. And so if you guys remember, group 1, called the alkali metals, they like to lose one electron, and therefore because they've lost an electron, they form a +1 charge. We call it a predictable or univalent charge. The alkaline earth metals were +2, so I'm referring vertically. We would skip over the transition metals, we'll come back to them, and then starting with aluminum, this carried a +3 charge. We typically skipped over group 14, and then group 15, because they have those 5 outer electrons, they liked to gain the electrons needed for the octet, and so they would gain 3 electrons, creating a -3 charge. The chalcogens, group 16, would be -2, the halogens, -1, and the noble gases are unreactive. Okay, so those are some univalent charges. And going back towards aluminum, some refer to these as Katzenagel, or there was like a 3-2-1 diagonal. So zinc always forms a +2 charge in a compound, as well as cadmium. And then silver forms a +1 charge when in a compound. It's going to always give away 1 electron. And then if you remember, everything else in the transition metals, and I'm careful over by the staircase because some of those, nope, just kidding. The staircase is included. That these were called multivalent, or they have multiple charges. They're not just a set one charge, or maybe some refer to it as they're unpredictable. And that's when we use the Roman numerals. If we were naming it to say, hey, iron could be +2 or +3, but in this compound, it gave away 3 electrons. So this is the front side of the periodic table, and let's check out the back side. Today, we'll be referring to the polyatomics that are found on the back side of the periodic table. They're grouped by their overall charge. So remember, to be nitrate is 1 nitrogen, 3 oxygens, and then the whole group or the whole polyatomic carries a charge. For this column, everyone carries a -1 charge. Then we have some that carry a -2 charge, -3 charge, and then we have 1 polyatomic ion called ammonium that carries a +1 charge, the only positive polyatomic. Okay, so let's start off actually with a review. Back in Unit 8, we taught you guys how to name acidic compounds. And so they were anything that started with an H. And so we said what's really attached to the H is how the naming system works. And so if it's just hydrogen attached to one other element, like chloride or bromide, then you're going to use the phrase hydroic acid. So for example, HCl would be named hydrochloric acid. Typically, this system works for hydrogen attached to something from the front of the periodic table. If you have something attached to hydrogen and that group name ends in "ite," like if you had sulfite, H2SO3, we swapped out "ite" for "us" acid. So this was sulfurous acid. And then if the group attached to the hydrogen ended in "ate," you swapped out "ate" for "ic" acid. So if you had HNO3, that polyatomic is called nitrate. It swaps out for nitric acid. So let me write a few practice problems. HF, HClO2, H2CO3. So considering that we're starting a unit all about acids and bases, you're definitely going to be seeing a lot of acids, whether in formula or name, so it's good to remember how we name them. So HF would be hydrofluoric acid. HClO2, that group is called chlorite, that polyatomic. So ite goes to us, that would be chlorus acid. And then the next one, that's carbonate, so this becomes carbonic acid. And let me just throw this one in there, HC2H3O2. It always looks intimidating because there's so many elements going on, but that group is called acetate, and so also known as acetic acid. Common name is vinegar. Vinegar. Not sure. Something that we didn't necessarily call it a base, but in our nomenclature unit, you did learn how to name this because it fell under ionic. Later in here, you'll learn bases typically end with hydroxide, with OH. So Mg, OH, Fe, so this would have just been under normal ionic compounds, and if you remember ionic, you name the metal, check to see if they need Roman numerals, and then you name the non-metal. And so this first base would be sodium, and does not need Roman numerals. And then OH is a group, a polyatomic called hydroxide on the back of your periodic table. MgOH2 is magnesium hydroxide. And then this next one would be iron. This is an unpredictable charge, so it's going to need Roman numerals. Hydroxide. And if you remember how to do Roman numerals, you work backwards. We know that hydroxide's -1, but there's 3 of them, so that's an overall -3. This iron must be carrying a +3 charge. And then like Unit 8, also be able to work it backwards, where we give you a name and you write a formula. So if we give you hydrosulfuric acid, we know acids have a hydrogen ion. Hydro indicates only one other element, which would be sulfur, which is a -2. So for this to be balanced, we need 2 hydrogens and a sulfur. For a base, it could be something like zinc hydroxide. Zinc was a part of that special staircase we sometimes called Katzenegel, but even though it looks like it's in the unpredictable charge, it always carried a +2 charge. Silver was +1, aluminum was +3. Hydroxide carries a -1. So in order to be balanced, you would need 2 hydroxides to balance that +2. And so parentheses, 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 that was what was most missed in Unit 8. So flashback to Unit 8, nomenclature does appear in this unit, but specifically about acids and bases. Okay, we're first going to focus on acids, and then we'll focus on bases. And so you can just highlight these in your notes, but we do want you guys to know properties that are distinguishable for acids. And one is that acids typically have a tart or sour taste. So you can see in our picture, like lemons, there's citric acid in there, and lemons have that sour taste. Acids, when dissolved in water, they're going to break up into ions, and so based on that, they can conduct electricity, and so they're called electrolytes, but acids conduct electricity when in solutions. Another property to know about acids is how they behave with an indicator. So by definition, an indicator, it's indicating if something is an acid or a base, and you'll see that by a color change. There are many, many different types of indicators. One of them that you'll eventually see in lab is called litmus paper. It's a piece of paper, and if you dip it into something that's acidic, the paper is going to turn red. And if the paper was red, it would stay red. Another type of indicator that you've actually already experienced in lab like last semester was phenolphthalein. And so you would drop a few drops in, and if it's acidic, the solution would stay clear. And then we're jumping ahead, but if it was basic, it would turn that pink color. There are a few natural indicators. One of them is cabbage juice. So if you kind of boil this down and get cabbage juice, the cabbage juice will change colors based on if it's acidic or basic. Hydrangeas will turn different colors based on the pH of the soil. And so that's kind of cool. If it's like basic, I think it's more purple, and if it's acidic, it has more of a pink color to it. Acids can be classified as strong or weak, and I would just say be careful with this term because I think we like to think that strong, we really are saying something's concentrated, like it's 12 molar, and weak is it's not. That's not what strong and weak mean, okay? Strong and weak has to do with how something behaves in water. So a strong acid is going to completely break up, ionize, dissociate, all mean that same thing. Versus weak acids are going to only partially ionize. So let's first just talk a little more about the word dissociate or ionize. So when a hydrogen ion breaks apart from the acid, dissociates, what happens to it? The hydrogen gets absorbed by water, making a hydronium ion. So for example, when hydrobromic acid is placed in water, this hydrogen is going to break off, it's going to ionize, but then it's going to get absorbed by the H2O. So then your resulting things would be a hydronium ion and a bromine ion. This is making the solution acidic. Okay, this next part is a little bit awkward in your notes. They want you to draw an arrow. So for a strong acid, H with the theoretical A, when it's placed in water, they want you to draw a one-way arrow. So that acid is going to completely ionize, 100% break it off. So with your bar graph, it started as an acid, and then it 100% splits up. Those are for strong acids. Comparatively, a weak acid, they want you to draw a two-way arrow. So when you place a weak acid in water, it's partially going to ionize. You're going to have a split from the hydrogen and whatever was the anion. But then you're going to see the reaction reverse itself, and it's going to go back to being an acid. So it only partially dissociates. How do you know which acids are going to completely break up in water and which are not? There is a rule that you have to memorize. So acids that are considered strong, there's three that we call binary, which is iodine, bromine, and chlorine. Hydroiodic, hydrobromic, hydrochlorine. Conveniently, they're all halogens in a row, kind of like the diatomics, I bring clay. Those three acids are strong, and any acid that has two or more oxygens compared to the hydrogens. So for example, H2SO4, if you compare hydrogens to oxygens, there's 4 oxygens, 2 hydrogens, there's double the amount, there's at least 2 more oxygens than hydrogens, that's a strong acid. First, if you looked at sulfurous acid, compare 2 and 3, there's only a difference of 1 oxygen. This would be classified as weak. So let me just give you a few more examples. What about HClO3? Okay, compare hydrogen to oxygen. The difference is 2, right? There's 1 and 3. So the difference is 2 oxygens. There's 2 more oxygens, so this is a strong acid. It would completely ionize, 100% ionize in water. What about carbonic acid? Would you label it strong or weak? Okay, if you said weak, you are correct. Carbonic acid is a weak acid. There's a 2 to 3. There's only 1 oxygen difference, and the rule says it has to have 2 more oxygens than hydrogens. What about hydrofluoric acid? If you said weak, you are correct. So notice there's not oxygens, that's this half of the rule, but the other rule is iodine, bromine, chlorine. Well, fluorine does not fit that category. Now, if I asked you about hydrochloric acid, this is considered a strong acid. This is something I would definitely star and highlight. It's easy to forget the strong acid rules. Okay, last thing about acids is a simple definition called polyprotic acids. We've talked about polyatomic before, poly meaning many. So this is an acid that has more than one, has many hydrogens it could dissociate. So HCl is not a polyatomic acid, but H2S, hydrosulfuric acid, is a polyatomic acid. It has more than one hydrogen that could break off. Okay, going to the other side of the spectrum, let's talk about bases. Bases have that bitter taste and a slippery feel. So a lot of household cleaners are basic products. I think soap or ammonia, Clorox are basic products. Like acidic things, bases also conduct electricity when in a solution. So a base can dissociate in water with charges that allow for a connection to happen with a light bulb and therefore conduct electricity. So remember, just like acids, we do want you to know the properties or characteristics of bases. In terms of indicators for a base, with our litmus paper, you're going to see litmus paper turn blue. And you're going to start seeing a lot of alliteration. Bases start with B, and you're going to notice bases have a bitter taste from our last slide. Bases turn litmus paper blue. In phenolphthalein, a basic solution, you drop a couple phenolphthalein drops in, it's going to turn pink. There are two types of bases, strong and weak, very similar to acidic in that strong bases 100% ionize or separate in water, and weak bases only partially dissociate. So for example, sodium hydroxide, when you place it in water, you're going to see 100% ionization. Ions are charged particles. You're going to see a complete breakup. How do you know which bases will completely break up? So who are your strong bases? This is a rule you have to memorize, and this is a very different rule than what are strong acids. So strong bases, you have to look at the periodic table, and any strong base is going to include a alkali metal or strontium or barium. And so if you notice, there forms like a little B on the periodic table. These are where your strong bases are. So lithium hydroxide is a strong base. Potassium hydroxide is a strong base because those are alkali metals. Strontium hydroxide is a strong base because it's in that little B. This is a little bit of a stretch, but if you, let me erase this. Strontium and barium, doesn't that almost say strong base? Like if you kind of fill in some letters. So barium hydroxide is a strong base. But if you were to go above strontium to like calcium hydroxide, well, that's in the blacked out area. That would be a weak base. It wouldn't completely ionize in water. Same thing for beryllium and magnesium or any metal over here. Okay, lastly, what happens when you combine an acid and a base is you actually form a salt. So I like underneath here, you have a base, potassium hydroxide, you have an acid, nitric acid, and it's really just a double replacement reaction. The two cations swap places, so K goes with NO3 and HOH, also known as water. So sometimes it kind of sounds scary of like, oh, what happens if you mix an acid and a base? Well, you end up, because acids and bases are on two different ends of the spectrum, they meet in the middle and they make a salt, as well as water. So we're going to kind of be bringing back Unit 10 using chemical reactions and balancing, but we're going to be only focusing on the reaction of an acid plus a base called a neutralization reaction. We're neutralizing the acid and the base. All right, guys, thanks for watching this video. If you turn your page in your notes or scroll We've split this lesson is a really big lesson, so we've split it over, we're splitting it into 2 different lessons, and so there's going to be some unfilled places the theories will come back to. But if y'all can find where your practice page starts, there actually is a second page to it. But for what we just went over today, we would ask y'all to practice numbers 1 through 15. Now, you don't have to practice every single one, but when we come back together, we will answer questions, and then this just gives you an opportunity to practice what we just went over. So good luck, and see you next time.